All right, hi everyone. So Laurent already gave a really, really nice intro to how we get astrometry with regard to especially the direct imaging case, of course. And so now I wanted to talk to you a little bit about how we take that astrometry and actually turn that into something physical that we can learn about the system. So going from measurements to orbits to learn more about our objects and hopefully say something about how they form or how they maybe even evolved early on. So just to start out, why do we care about orbits? Ron talked a little bit about this too, but basically understanding the orbital properties of these directly imaged planets that you've been learning so much about this week really provide powerful constraints on their evolution. And this is demonstrated, of course, here with this beautiful image taken of Betapic showing both of the detections on one side of the star and then the other, and of course how that already told them so much based on the fact that they expected this a little bit because of the orientation of the disk, but then they can basically connect the orbit back to the disk and say something, provide constraints on the evolution of the planet with respect to the disk. In addition, you've also heard a few people say that, of course, orbits are the only way to directly empirically get masses, so that's a really important aspect as well. That's a little bit, in terms of the directly imaged planets, sometimes that gets swept under the rug a little bit because often we fix the mass when we fit the orbits. But in general, orbits are very powerful for getting masses as well if you have enough information. In addition, just looking if you can get a good handle on some of the orbital properties or the distribution of orbital properties of the images that you're looking at, you could maybe even say something about it can trace the formation of the planet or even be a tracer of subsequent dynamical processes. And this is really important for directly imaged exoplanets where we're seeing them at really large distances from their host star, and you don't necessarily have good formation models that can explain the existence of these very large planets out at large distances. So, for instance, it's been suggested that maybe some of these planets were able to form closer in and then were scattered out via multi-planet interaction. And in this simulation done by Chatterjee et al. In 2008, what they did was looked at a close-in triple planet system and let it dynamically evolve, and saw that in many cases, two of the planets would survive and one of the other ones would be ejected or would die somehow. But there would be a distinct signature in the eccentricities of the surviving planets that would show that it did undergo this dynamical interaction. So you can see here they've plotted eccentricity as a function of separation, and so all the black dots are for the surviving planet that's closer to the star, and the red dots are the surviving planet that's more distant from the star. You can see as you're starting to push out to these larger and larger separations, out to the places where we're seeing these directly imaged planets, all of the objects in their simulation have very high eccentricities. So if you can actually measure or get at least an upper limit or some sort of handle on the eccentricity of your planet, you might be able to say something about how it formed close in and then scattered out. And then finally, we're not even near the ability to do this yet for direct image planets, but this is something really cool that's been done with Kepler data, is that if you can identify, in particular in multi-planet systems, evidence of resonances, you can possibly say something really interesting about the early migration history, for instance, of widely separated exoplanets and other things as well. So this is the results from the very famous results from Kepler that show just the number of objects with different period ratios all piling up right around these resonance points or integer period ratios. So the 3-to-1, the 2-to-1, et cetera, et cetera. And there's tons of work on the dynamics to explain why these things are also near resonance but not exactly at resonance. So once we start with these big surveys, maybe to find more directly imaged planets, maybe we can do something similar to this as well. This is another method of using orbits. So hopefully that gives a little bit of motivation to why we're interested in doing this and not just doing all this huge amount of analysis to get this very precise astrometry just for fun. So now what I want to do is spend a little time going through some of the equations that we use to actually fit orbits, and a little bit of derivation. So I'm going to get a little bit mathy. This is probably the mathiest talk I've ever given. So I apologize if you all want to go to sleep. It's sort of early in the morning. But if nothing else, if you find orbital dynamic math totally boring, just remember these references or look these up later. These are super, super good, really helpful references for getting the equations for fitting visual binary orbits, and also for explaining the physics of where these numbers actually come from and these equations come from. So we can't talk about orbits without first at least talking about Kepler. So of course, Kepler did some of the very earliest analytic descriptions of orbits, but of course he didn't he was mostly doing this all empirically. He didn't really have a good explanation or understanding of why his laws worked, but he did derive them. Back in 1609 and 1619, he came up with his 3 laws of planetary motion. So I just wanted to remind everybody, do a little review of at least what those are, because those are often used by us and they're very important. So of course, the first law is that, at least in terms of he did this all in terms of the planets in our own solar system, so they're all related to the sun. So a planet, the orbit of a planet is an ellipse with the sun at one focus. So here we have a beautiful ellipse. Here's our planet. And there's the sun. So he noted early on, of course, that our orbits are not all circular. They're, in fact, elliptical. And then the second law is one that it took me a while to actually understand. But if you have a diagram like this, it's much easier. So the planet, as it orbits, doesn't have a constant velocity, but instead has a velocity such that the planet is sweeping out equal area in equal time. So it will take equally as long for the planet to go from here to here in this little area wedge as it will from here to here and here to here. So it has to move faster at this point in its orbit in order to obey this law. So that's the second law. And then the third law is that, the one I use the most often probably, is that the period of a planet's orbit squared is proportional to its average distance from the sun cubed. So this is shown in this, when Kepler did this, these two weren't even discovered. So you can pretend you don't have those. Here's the cube of the semi-major axis versus the square of the orbital period. And you can see it follows this nice line. He saw this as a proportionality. Of course, we know that these are all related to each other through the mass of the system. But we know that now. So the actual physical understanding of this didn't come until we had more modern understanding of orbital mechanics and Newtonian gravity to explain why these laws actually worked. So basically, starting from the beginning, so we have a particle that's experiencing a conservative force pointing this way. The particle is moving like this. It's separated from some sort of center or object by a distance r. And it has a velocity r dot. So if we look at angular momentum, it must be conserved. So we have mr across r dot equals a constant in this case. And this is actually useful because you can see that the direction or the direction of the angular momentum is actually proportional, or is actually normal to the plane of the orbit. So your orbital plane is completely defined by the direction of your angular momentum vector. And that actually helps explain what I'll talk a little bit about later about why some orbital parameters are easier or fall out quicker based on the number of measurements that you have. It's because it's often easier to get an estimate of the angular momentum early on. So now let's look at that in a little bit more detail and understand a little bit about what the actual equations of motion are for a body operating under a central force. So your body it starts here at point P1, and it's moving to point P2 along some orbit. So it's based on some origin. It has an initial distance of r and a new distance of r plus r dr. So we'll talk about that. So the planet moves from P1 to P2, goes r plus dr. And then it also has another component of its motion in theta. So it starts out at theta and moves to theta plus d theta. I know this is a little bit hard to read, so I apologize for that. That's why I wanted to blow this up here. So what are its actual velocities of the components? So the velocity in this direction and also in the tangential and the radial direction is described by this equation here. And it actually helps to look at the orbital speed. So this is something that comes up a lot in using orbit equations, where you plug different things into this and get out different aspects to explain the speed. So this is what the speed of the orbit is at any given time. And then, now if we look at instead of the acceleration, we can finally get to one of Kepler's laws and derive it actually. So here, if you take the second derivative of this is the acceleration of the planet. And this is the radial component of the acceleration, and this is the transverse component. So I'm doing this for a reason, I promise. So you have these two different components of the acceleration. Let's look at this again. So now we can actually take the fact that we know what the magnitude of the angular momentum is. It looks like this, and that's actually a constant, which we showed before. And so we can actually plug this in and do some math. So if we actually take the time derivative of this, and divide 1 by 1 over r, we get out this component, which is the transverse component of the acceleration, and we see that that's equal to 0. And so why do we care about this? Well, because it makes sense that because we understand this force, the direction of the acceleration should be all radial. But it's actually interesting when you're trying to determine whether in your astrometry you've actually detected an acceleration or not, because it's actually difficult to do. One of the things you need to make sure is that you actually have no transverse component in your accelerations, because then it probably implies that you haven't detected it yet. So I'm going to talk about that a little bit later when I talk about examples of this. And this also gives you Kepler's second law as well through this. So if we use this again, so here's our angular momentum. If we actually look at what the equation for area is of this little wedge here, this is what the equation for the area is. And then if we take the time derivative of that, that's how you end up with Kepler's second law, because you get that it comes out to be equal to the same thing as the angular momentum, and you know that's a constant. So it's equal area and equal time. Let's see. Okay, now let's talk a little bit about conservation of energy. So this is what the equation for conservation of energy is. So here's the kinetic energy, and then here's the gravitational potential energy, which we know from Newton's laws. Those should be constant. And then you can do lots of algebra that I'm skipping now, and show that you can actually derive a form of the radius to figure out exactly the value for the radius at any given time in your orbit, and it's equal to this parameter L divided by 1 plus the eccentricity times the cosine of this angle. So eccentricity is something we're familiar with. It's kind of the squishiness or the ellipticity, I guess, of your ellipse or your orbital ellipse. And so for bound orbits, we look at eccentricities of less than 1. So I'm only going to talk about bound orbits because we're assuming most of our planets are bound at this point. It could be interesting in the future to look at unbound orbits, maybe for things that could be flying out of the system. But right now we're just going to be talking about bound orbits. And this parameter L has this like super unfortunate name called semi-lactus rectum. I'm like, oh man. But it's actually it's just the angular momentum divided by the gravitational constant times the two masses. So if you do a whole bunch of math, you can actually get this out. And this shows you, this is Kepler's first law, because this turns out to be an equation for basically a conic section. So you know the shape of your orbit is elliptical. Okay. And I'm going to totally gloss over the derivation of Kepler's third law. But first, just to make sure we're all on the same page, what is the semi-major axis? I've been sort of referring to it. So the major axis of this ellipse here is the long axis, basically, and the semi-major axis is half of that. And then for sometimes you see also the semi-minor axis, and that's the short axis of the ellipse, basically half of it. And if you combine the previous equations, you can actually derive this, Kepler's third law, which is that the mass is actually equal to 4 times pi squared times the semi-major axis cubed over the period squared. So this is, of course, the period is the whole time it takes for the orbit to be completed. Okay. All right, so that was mathiness. So I'm going to pause from mathiness for a second. So with direct imaging, so I've been showing like R dots and all this different stuff. But what do we actually measure? So this is what we measure. Laurent was just talking about it. So we have our star, and then we hopefully have our awesome discovery of a planet. And we just measure the relative separation between these two. So the difference, so we have a delta x and a delta y. So you could do it in r and theta, but actually since our detectors are basically square grids, usually our real measurements are of x and y and some sort of time. And if we're lucky and the TAC likes us, we then get to go and get a second measurement, and then we get x2, y2 in a second time. And so because we have two positions and two times, we then have a velocity measurement, one velocity measurement. And if you're super lucky, you get to keep going back to the telescope and getting more time, more x's, y's, and times. So how do we go from all of the stuff I was showing you before, the physics of these orbits, to something that we can actually compare to projections of the motion on the sky? So now I'm going to talk about that a little bit. Yeah, what I said. Okay. So the first thing I wanted to talk about was the fact that what we know about orbits is that this is a very fortunate thing for radial velocity discovered planets, is that planets don't just orbit their sun. The two actually orbit each other and orbit their common center of mass. So I wanted to talk about how you go from the true orbits, where things are more orbiting the center of mass, to a relative orbit, which is what we need to look at for visual binaries or visual double systems. So in this little diagram, you have your source here, P1 and P2. So those are your two orbiting objects. They're orbiting their common center of mass at point C. The separation from the reference point of this one is R1, this one is R2, and the separation between both of them is just regular R. So these are the two equations that you probably are quite familiar with that describe their motion of each of these around the common center of mass. So what we're really interested in is basically the relative motion of one with respect to the other. And so if you do some math, you get this. So you get the difference between this and this, which is just R, is equal to the gravitational constant times the two masses added together divided by the radius squared. So it's important, and this is partially where it comes from. So relative orbits, where you only measure the relative motion of one component with respect to the other, will only give you the total system mass. So you can't get individual component masses just from astrometry alone. You have to have some other piece of information, like radial velocities, for instance, which I think Justin talked to you a lot about before. So this is partially where this comes from. But how do these actually relate to each other? So if you do have some sort of information that tells you where the center of mass is, or somehow maybe background reference sources, how do you actually relate these two kinds of orbits to each other? So they're actually easily related through a few different, in terms of their semi-major axis and eccentricity. So the semi-major axis of their relative orbit, the one that you're measuring, is actually equal to the semi-major axes of the individual orbits of the components added together. And actually, as you can see from this nice diagram here of these two objects orbiting their center of their common center of mass, the ellipses are about the same amount of squishiness or ellipticity. So actually, the eccentricities of all three orbits are exactly equal to each other. And then you can actually, there's a good ratio between the semi-major axes, which are fairly easy to measure, and the actual component masses and the total system mass. So you can see that the A1, A2 to A relative ratio is equal to M1 to M2 to the total system mass. So this is something useful in case you actually have the ability to convert between the two kinds of orbits. Okay, so now I'm going to start to define the actual orbital parameters that we fit when we're actually doing the fitting. So I've already talked about a few of them. So I talked about semi-major axis and I talked about eccentricity. But now there's some important angles that we need to know. So this diagram shows how these angles are actually defined, and I find them like a little bit confusing, so bear with me. I have to stare at this diagram a lot, even though I do this a lot. So again, here is our orbital ellipse. So our planet is orbiting around. It's at point P. It has a radius from the sun or the star that you're looking at right here that's shown by this. And this is the point. And so it has some sort of angle theta. And that angle between the axis line and the point where the planet actually is called the true anomaly. And this is an actual difficult angle to actually measure. So they do this super complicated thing to define an angle that's slightly easier to measure, which is the eccentric anomaly. So what they use is this circle here is called the auxiliary circle, and it's defined as a perfect circle that has a diameter that's the same as the or the same as the major axis of the ellipse. And so you can see there's a point on this auxiliary circle called Q that's basically directly above the point P where the planet is on its orbit. And the angle between this point Q and the very center, or the reference point of the ellipse, is called E, and that's the eccentric anomaly. So that's something we hear a lot about. This seems like a lot to go through, but again, this is easier to calculate in many ways than the true anomaly is. Some other important points from this are the periastron and apoastron. So the periastron is the closest distance that the orbiting pair will have. And so that is defined right here. It's usually shown as pi. So when the planet is here, it will have its shortest separation from the star. At apoastron, it's at the furthest distance, so that's shown here as A. So how do the true anomaly and the eccentric anomaly relate to each other? So this is what's shown here. So they're related by their tangents and also by this fraction of eccentricity to the 1/2 power. So you can go between the two. If you can measure one, you can get the other as long as you know the eccentricity. And then if you do, again, I'm skipping over a ton of math, but you can actually derive an equation for the radius of the relative separation between the star and the planet at any given time here. And so it's just defined as the semi-major axis times 1 minus the eccentricity times the cosine of the eccentric anomaly. So that's part of the reason why this angle is so nice, is because it breaks down into this fairly straightforward formula. As you can see, the periastron and apoastron distances are special places where you have a fairly straightforward equation that you can use to find them. So the periastron distance breaks down to just being the semi-major axis times 1 minus e, and it's the opposite for the apoastron distance. So those are some nice little things to remember. Let's see. So how do you actually solve for the eccentric anomaly? And this is something that's really important, and basically everybody has to do when you're fitting orbits, is figure out a nice way that you want to solve for this angle. It can actually be solved for using something called Kepler's equation, which I'm showing right here. So it's e minus little e sine e is equal to 2 pi divided by the period of the orbit times the time you're looking at the object minus reference time. And usually we define this reference time as the time of periastron passage, so the time when the planet is actually at its closest approach. So this is one of the orbital elements as well that people try to measure. So as you can probably tell, there's no analytic solution for this equation. So Kepler's equation is transcendental, which means that it has to be solved numerically. So I'm not going to go through the numerical ways of solving this, but you could look up, for instance, this kind of iterative solution method that you can use to solve for this. Okay. All right. So now we're going to go through and define the last few of the orbital parameters that I haven't talked about yet. So here's how, so we have to remember that we're looking at a visual binary or visual star-planet orbit projected onto the plane of the sky, and I think this diagram actually does a nice job of showing how that projection looks. So here we are as the observer on the Earth, and we're looking this direction towards the orbit of some object, and this is what the true orbit looks like. But it's when you project it onto the plane of the sky that we actually observe with our telescope, it looks like this. Okay. One more robot. I'll hold it. Is that better? Okay. So the reason I like this this image is because it actually gives you a nice idea of what inclination actually is. So you can see the inclination is the angle between basically the true orbit like this in the plane of the sky and what we actually see. Another thing that is nicely defined by this image is the point called the ascending node and the descending node, which is over here. So this is the point at which the orbital plane and the plane of the sky, or the plane of the celestial sphere, meet each other. And ascending is defined basically as where the planet is moving the most quickly away from us, and descending is where it's moving towards us. And this is important because it helps us define an additional orbital parameter called the longitude of the ascending node. So now I'm showing you a diagram that I think is actually harder to interpret, because now our eyeball is under here looking up, but it actually has a nice demonstration of all the different angles. So we have a broken, there we go. Here's our inclination again. Here's N, oh wow. I've never had so many technical difficulties with this stuff. So here's the point, the ascending node. You can see that this longitude of the ascending node is basically defined as this angle here at the point at which, so basically you have inclination that's like this and the longitude of ascending node that's like this. So that defines perfectly the orientation of your orbital plane. The other important angle is the longitude of periastron passage. So this is, again, is our orbital ellipse that we were looking at before. And so here's pi, where periastron passage actually happens. And you can see this is the angle between this line here and the point at which that happens. So that gives you another reference point for the angles that you're going to use to fit for your orbit. So all of inclination and both of the big and small omegas coupled with the semi-major axis are actually called the geometrical orbital elements. And these are some of those that we usually fit for. And then you combine those with what we call the dynamical orbital elements, so things I was talking about before, like the period, the time of periastron passage that was defined in Kepler's equation, and the eccentricity. So altogether, those are the orbital elements that we usually fit for when we're doing this kind of work for these directly imaged exoplanets. Okay, so I keep saying, like, how does this relate back to what we actually measure? So just as a reminder, again, we measure the relative separations between the star and the planet, so x's and y's at some given time. How do we project this into these actual orbital elements that we're interested in measuring? So here's how we project these on. When you project the orbit onto a 3-coordinate axis, all 3 of these are dead. They're just playing a game with me. I'm just going to pick up a new one, and then it's going to die, and I'll pick up another one. So this is how X, Y, and Z look in Cartesian coordinates, basically. So you can see that there's an R in these equations, and most of them have the angles that we were talking about, the omegas and the inclinations, but you can also see that there's a true anomaly in these equations as well, so we want to get rid of that if we can. Also, in general, like I said, we generally tend not to have information in the Z direction, unless we have some sort of radial velocity information. So for the most part, when we have just astrometry, we don't have any information about Z. So I'm going to ignore Z after this and just talk about X and Y and what we can get from X and Y. So there are these really, if we want to, we can actually do more math and switch to and define some constants that are really, really useful for fitting orbits that I think you guys might find useful in the future, so this is a good reference. They're called the Thiele-Enes constants, and they're these A, B, F, and G. And you can see that they only depend now on the geometrical orbital elements that I was talking about. So they have just the semi-major axis, and then various sines and cosines of the omegas and the inclination. There's also these elliptical rectangular coordinates that contain the dynamical orbital elements down here. So these are the geometrical and these are the dynamical, and those are defined as big X and big Y. You can see that they have the eccentric anomaly, which has the period and the time of periastron passage in it, and the eccentricity is here. So it has all the dynamical elements. All right, after all this mathiness, we end up here. So X at any given time can be defined as just the multiplication of these different constants. So, or not constant, the B and G and A and F are constants, and then X and Y are your coordinates that have your dynamical information. So this breaks down into fairly simple equations that you can actually use now to go and finally do your fitting after you have all of this, have gone through all this math. Okay. All right. So that ends the mathiness. So if we have our equations, we have a vague idea of where they come from with physics behind them. So what are some of the methods for solving for these and calculating these? I'm not going to go into detail about these different methods. It's sort of like Laurent said, where there's all of these are good, and people have different methods that they choose. So I encourage everybody to kind of look up. Every paper on this has a slightly different way of doing this analysis. So you can use basic just chi-squared minimization. Often you find that the parameter space is a little bit too complicated for this, so you have to do some sort of chi-squared minimization in combination with a Monte Carlo to really sample the parameter space. Markov chain Monte Carlos are really, really popular. I think Justin might have talked about this a little in his talk, how you actually do these. There's another advanced kind of Markov chain called multinest and others that I encourage everybody to look up if they're interested in doing this kind of work. I'm not going to spend too much time about it because I've already been too mathy. So now I want to talk about orbits in action and actually show some examples from recent works about what we've been able to get out of orbits from fitting the astrometry. So this has been mentioned before. Again, Laurent mentioned this too. But it's important to remember that directly imaged companions generally are very widely separated, so they're on very long period orbits. So this is just an example of what it would look like if you saw a circular face-on orbit with a semi-major axis of 30 AU at a distance of 30 parsecs. So here's your full orbit. And if you were lucky enough to actually get to measure this planet for 10 years, you would still only have this tiny, tiny little fraction of orbital phase coverage. So there are some people that think you basically need a huge fraction of the orbit to do anything useful with orbital fitting. That's not entirely true. But what is true is that best fits in this case are not generally interesting on their own because there's a lot of best fit orbits with very similar chi-squared or whatever other metric you want to use that could pass through these data points. But instead what we try to figure out is the distribution of allowed orbital parameters based on the astrometry for these long period binaries, which can again be useful for trying to constrain things like high or low eccentricity, for instance, to rule out maybe if they were dynamically scattered, et cetera. So you can still do orbit fitting even though you only have a tiny bit of coverage. So the first example I want to talk about is the PZTell system. So it's not a planet, but it's actually a brown dwarf that was discovered with Nikki back in 2010. They had nice images at JH and K. So this is from Beth Biller's paper. PZTell, I think, is about 35 Jupiter masses or so. And one of the interesting things they did in this discovery paper, so usually in a discovery paper you have your initial discovery epoch, and then you do your common proper motion follow-up like Laurent was talking about to see if it's actually bound. But they were able to actually get orbital information from just 2 measurements alone. One of the tricks that we usually play for direct imaging is that you can allow the mass to be a free parameter or you can fix it. And because usually the mass of the star is so much more dominant over the mass of the planet, we often will use an estimate of the mass of the star from something else, like from a model or anything else that you might have, to constrain the parameter space a little bit. So that's, I think, almost everything I'm going to be showing you. They've fixed the mass of the star in this analysis. But when they do that, they actually can take just these 2 measurements and sample through a bunch of different inclinations and the 2 omegas that I was showing you. And they actually were able to find that the eccentricity of the system should be relatively high based on only these 2 epochs of measurements. So here's their 2 sigma disallowed orbits. But when you get additional data, you can do a little bit better. So this system has been continued to be followed down at NAKO, with NAKO in the VLT. And so this is work published in 2012. And so this now is the same diagram. In this case, these authors used what they called a least squares Monte Carlo. So they did the combination of the chi-squared minimization and Monte Carlo sampling. What they're plotting here are the solutions that they get as a function of reduced chi-squared. So everything that has a good chi-squared is shown in purple, and the poorer chi-squareds are in red. But basically they get the same answer, even having more data. I think they have about 6 data points or so. That the eccentricity of this system is probably high, and that it may have, for it to not have an almost super, super eccentric orbit, almost with an eccentricity of 1, it needs to be close to edge on. So that might be another constraint as well, that we might be viewing the system actually close to edge on if we don't think it has this really high eccentricity. Okay. All right, so we've already heard a little bit about Betapic, obviously. I talked about it a little bit. Discovery image of Betapic with NAKO back in 2009. Betapic is interesting again because it might have been assumed based on the orientation of the disk that it could be close to edge on, and indeed that does happen to be the case. So they followed it for a while. There was this time period when you couldn't observe it for a while, and it was sort of sketchy. But then it popped back out from the other side of the star, showing that it is indeed very close to edge on. Here's all their measurements. So what they've done is project it to have basically a face-on view, so you can see the points easier. But from our vantage point on the Earth, we see almost a straight line of motion. And so they have here 2 different orbits that fit through the data. And you can see just how nicely, actually, they've done on their astrometry. They get really, really good fits to the data. A slight update for this. So this target was, of course, observed with GPI, and we did a little bit of orbital monitoring as well, or orbital modeling as well. What we found was that the orbit of the star, the planet had reached its furthest point in its orbit and had turned back around. That point is called quadrature. And so that allowed us to look, and this is a different way of looking at orbits. So now you're looking at the change in the x and the y position as a function of time and the different orbits that pass through it. The most interesting part about this, I think, is that we have constrained this to have about a 4% probability of transit in 2017, which I think is probably high enough for people to devote a lot of telescope time to this. I'm not sure. But most likely, what you get out of a transit is enough for 4% probability, I think. Okay, now I'm going to end with my favorite example, which is HR 8799. We've already heard a lot about this. Here's the properties of HR 8799. Because it's a multi-planet system, you can get additional information after you do figure out what's astrometrically allowed in terms of your orbits. So I talked about this a while ago. Hopefully everybody didn't forget that you can actually try to say, it's important for these long period objects to try to say when you think you finally detected accelerations. So what we did is we thought, we looked at all of our data from 1998 all the way up through the most recent data, which is about 14 to 15 years worth of data. Still not a huge fraction of orbital coverage, but some. And we think we were able to actually detect acceleration for HR 8799C and D. And we did that by basically getting a 3 sigma measurement of acceleration in the radial direction, but 0 in the tangential. So if we hadn't had sufficient data with good precision, we would have had a tangential velocity that wasn't 0, and that would have told us that either we don't have enough data or something's wrong with our astrometry. So this is, again, a nice check of your measurements as well. So here's what some sample orbits look like fitting to the astrometry. Most of this is from Keck. Some of it is also from the Hubble data points that Laurent was talking about before. There's 15 years of orbital coverage, again, a tiny fraction of the orbit, so not particularly interesting on its own. What we look at instead is the fraction or the families of allowed orbits. So when you look at these all together, you can see sort of the swaths of orbital parameter space that are swept out. And this is all done by fitting those equations that I was showing you before. And you can make really cool plots, but you can also get interesting information as well. So often when you look at these orbit papers, you'll see things that look like this. They might be slightly more legible, I'm not sure. But you'll see every orbital parameter plotted against every other orbital parameter. And it shows you that the parameter space is highly non-uniform and has these weird, interesting degeneracies with different parameters. Fitting orbits is complicated, and you need to make sure that you take into account all of the different uncertainties, which is why people tend to use Monte Carlo methods. And I just wanted to mention this again because I mentioned it in the first place. It's often easiest to get things like the inclination constrained first. So the tightest constraints can be on the orientation of the orbit. And that's, again, because it's completely defined by the angular momentum vector. So if you have some sort of estimate of the direction and of the orbit and the direction of the velocity, you actually get inclination quite quickly. I'm almost done. I just wanted to say really quickly, oftentimes you can use other information to try to do a better job constraining your fits, like the orientation of a debris disk, like they did for Fomalhaut. Or you can use dynamics to try to constrain the masses if you have multi-planets. So this is just showing a dynamical simulation of the planets. Most of the time they fall apart like this. So it actually gives you limits on the masses as well, separate from actually fitting orbits. Okay. I'll just go through here to the conclusions, because beeps scare me. So orbits are a super powerful tool to help you understand directly imaged planets, and precise astrometry can really help you to directly map the orbital parameters. And I think once we have more directly imaged planets, we'll be able to say something about the bulk parameters in general through these kinds of methods. So thank you. Where does the a directly imaged planet with a transit measurement would be the best thing ever in the history of ever. And so how are we going to refine the percent likelihood of it transiting? And that'll happen with more measurements. So there's ongoing monitoring programs as the planet moves back in close to the star, and every measurement should give us an improvement on that. And so unfortunately, I think the probability will go down, but hopefully it'll stay high and we'll be actually able to get something interesting. Yeah. When you fit the outer planet, you have to take into account the impact of the inner planets on the motion of the barycenter of the star, and I think the answer is, I don't, and I think the answer is it's below our measurement threshold, the motion of the star, the central star. So no. The constants have the semi-major axis in them, so how do you convert from arc seconds to AU or something physical, and how does the uncertainty in the distance impact you? It has a huge impact on you, especially in terms of if you want to know the actual mass of the object. So usually when we're doing these large Monte Carlos, it usually accounts for distance uncertainty, and that's part of the reason why we do them. And then the second question, was that enough answer for your first question? It has a really big impact, so the distance uncertainty is a big deal. The second question was, isn't there degeneracy between I and big omega? Yes, that's true. I think for inclination, it's defined, it's sort of fixed to be defined based on the way that the object is moving. For big omega, there's a degeneracy that you can't break unless you have information in the z direction. So if you do have some sort of radial velocity information, you can break that 180-degree degeneracy. That's the answer. Yes. Yeah, so you usually you either have a bimodal distribution, basically, if you don't have RVs. How tight are the mass constraints from the dynamical n-body simulations? I think people have basically had no success with anything above 7 Jupiter masses. And even then, it's hard. Usually you have to have them in resonance. So I ran out of time, but...